much. So I'm going to be the first of the three of us, and you guys are going to be the audience now. I'm going to start by giving you an overview of the issues we think about when we think about climate and coastal resilience, what we know well in terms of the science and what we're less certain about. And then I'm going to talk about some of the research that we've been doing for the last 3 decades at the Virginia Coastal Lab. And then you'll see there'll be sort of a natural segue to Phoebe Chrisman and then to John. I'll just say at the outset that we actually all, even though we're in 3 different schools, we work together. And that's one of the great things about UVA is it's very easy to work across schools. So I hope you'll see some synergism in the different things that we'll be talking about. So I don't know how. Did you not? Here we go. There we go. And do I have control on the lights? I think I must. How's that? There we go. So you can see a little bit better. OK, well, the combination of sea level rise and storms causing recurrent flooding in coastal areas is, I would argue, is probably the biggest effect of climate change that affects the greatest number of people. We know that over half the world's population lives on the coast. 11 of the 15 of the world's largest cities are also located on the coast. And they produce 61% of the global GDP. In the US, well, globally, it's thought that with the effects of sea level rise and storms, within the next 50 years or more, about 200 million people may be displaced along the coast. So it's a problem that's affecting a number of people. There we go. So there are 2 things I mentioned that affect us with regard to climate change along coastlines. The first is sea level rise, or global sea level. And the second that I'll mention is storms. And what this shows you is a record of sea level rise from the 1800s to here's the present, projected to the year 2100. And we have different ways of estimating that. Currently, we do it using satellite data. Before the advent of satellites, we used tide gauges out in the oceans. And then before we had tide gauges in the 1800s, we used what we call proxy records, which essentially we look at the skeletons of corals, and they grow as sea level increases. So we can reconstruct sea levels from those data. And so this shows the pattern that we have. And the projections are between 1 and 4 feet from our global models, with a possibility of as much as 6.6 feet of sea level rise by 2100. And I'm going to talk a little bit in a second about what's causing this change. These are different models that are being used. The big uncertainty here is related to the melting of the polar ice sheets. So this might not seem like a lot if you just look at a foot, but I'll show you some pictures in a second to try to convince you that it is something we need to be thinking about. Many cities and regions are already dealing with recurrent flooding. But the other thing I think to put it into perspective is from the present to here is 1 generation. So a kid born today would see between 1 foot and maybe 6 foot of sea level rise in their lifetime. So that's significant. The other thing we often think about is, OK, well, we know what we have some records for, but what about sort of deep Earth history? And there was recently a study that came out that was, again, using these proxies, was able to reconstruct global sea levels. And this shows sort of the variation over the last 2,500 years. And here's where we are now. So from these data, and these are collected globally around the world, we have both the highest rate of sea level rise, but also the highest sea level that we've seen, at least in the last 2,500 years. And this is causing recurrent flooding. These are some pictures. This is Venice. You probably all can recognize that. And this is Virginia Beach. So why are sea levels rising? There's two main reasons. The first is that the water, it's just physics. The water's getting warmer. As water gets warmer, it expands. As water expands, it takes up more space, and the sea levels rise. So water has this great capacity to absorb heat. It absorbs the oceans cover about 75% of the Earth's surface, and the oceans absorb about 90% of the heat that's captured in the atmosphere. So they're really a great sink for heat that we generate. It accounts for about 40% of that global sea level that I was showing you. And that's, as I said, that's physics. That's pretty certain. We have a really good handle on that. What we're less certain about is how the second factor, which is just basically the melting of ice on land. You've probably seen lots of pictures like this that show receding glaciers over a century or 70 years. And we see this in different parts of the world. This isn't actually that important when it comes to sea level rise. What's more important is the melting of the polar ice sheets in the Greenland and Antarctic ice sheets. And so in Greenland, we have a pretty good sense of how those ice sheets are melting and what that's adding to the global sea level. We do it by satellites. In Greenland, the ice sheet is sitting on the land, so it melts along the edge. And so it just recedes, and we can measure that quite accurately. And so here's an estimate. This is sort of seasonal variation, but here's an estimate of the change in ice cover from 2002 to 2016. Since 2002, we've lost about 3,500 gigatons. And if you're like me, you're like, what the heck is a gigaton? It is equal to 200 billion elephants. So that's like a lot of elephants in terms of mass of ice that's being melted and adding to the sea level. So again, we know that pretty well because we can measure it with satellites. What we're less certain about, and what's that difference between the 4 feet and the 6.6 feet, is what's going on in Antarctica. And so what's different about the ice sheet in Antarctica is it sits partly over the landmass, but also extends way out into the ocean. And so what happens is that as the seas are warming, it's also melting underneath. And we can't get that with satellites. We don't have a good way of measuring that. And so we do it through models and through calculations that we can do. But what happens is as the ice gets thinner and thinner, it can break off. And that can be a big pulse of water that causes sea levels to jump up. And I don't know if you all heard about this in the news last fall, but there was a lot of talk about this big crack that was in the ice sheet in Antarctica. And scientists have been monitoring this. There's an area about the size of Delaware that's breaking off. And estimates are that just that one event would cause global sea level rise to jump up 4 inches. Okay? So again, there's a fair amount of uncertainty in this, and this is what scientists spend a fair amount of time trying to understand. My point is simply that there's a range, and there's a reason for the range. There's things that we know well and things that we can model to the best of our ability. Okay, so in the U.S., most regions have seen up to 8 inches, between 4 and 8 inches of sea level rise just since 1960. And again, it might not seem like a lot to you, but if you think about the coastal plain of Virginia, you add 8 inches, and then in another 50 years, you add another 8 inches, and another 50, you add another 8 inches, you're having a lot of area that's being flooded. And so obviously we know of Louisiana as being a hot spot of sea level rise. There's lots of variation. And also coastal, the mid-Atlantic is. And this is little, but I just reminding me to tell you that we have sea level rise rates in Virginia that are double the global average. So it's significant in Virginia. So what would it look like? Here's the coastline now, and the light blue is the coastline with just a foot of sea level. Okay? So again, that's the lowest estimate. So I'll just go back, that, and that. So that's a lot of area that's being flooded. You can imagine if you go to 4 or 6.6 feet, that would be more, have a bigger effect on a greater number of people. So the last thing I want to do by way of introduction is talk about storms. That's the other thing that's affecting recurrent flooding in coastal areas and damage to coastal infrastructure. So the big question is, will storms become bigger, more frequent? There's some debate out in the science community with regard to that. I will tell you that we have a good record of our region of the North Atlantic. And well, this is just a statistic about Hurricane Sandy. It caused $68 billion in damage, and almost 150 people were killed. But again, some data just showing you that even though there's lots of variation from year to year, we are seeing an increase in the frequency of storms in our region. In Virginia alone, we're seeing 15 more storms a year than we did when the record started in the late 1800s. Okay? So it's an issue for us here in Virginia. So again, double the sea level rise and 15 more storms per year. The other thing about Virginia that's very unique is we have at once the longest, wildest stretch of coastline on the Atlantic and Gulf Coast that's here along this, the Delmarva Peninsula. And we have one of the most vulnerable urban areas in the world. So I'm going to switch now to talk a little bit about the research that we've been doing for the last 3 decades on the Eastern Shore. This is the, This is the Coastal Research Center that's located right here in Oyster, Virginia, that was built in 2006. So we've been looking a lot at how healthy ecosystems are the first line of defense, as it were, to the effects of sea level rise and storms. And so we look at salt marshes, oyster reefs, dune barrier islands, and then these underwater seagrass meadows, which is what I personally work on. So this is a picture of one of the barrier islands. You can see here all of this is storm overwash. This is sand that's washed over from a storm over top the dunes onto the back of the island, and it helps build the island. These islands are sort of slowly marching towards the mainland as sea level rise and storms are affecting them very naturally. We also see that wetlands are very important in both absorbing flooding waters and protecting coastal communities, but also reducing the wave energy that would be hitting the coast and causing erosion or damage. So one of the things we've learned is that wetlands, at least in this area, are really good at keeping pace with sea level rise. And they do that by capturing sand and growing in elevation as the seas are increasing. And they have really good mechanisms to do that. But they can also reach a tipping point. They reach a limit, either because there's not enough sediment, because rivers have been dammed, or because sea levels are rising faster than their ability to keep up. And so what happens is something like this. They reach the tipping point where they begin to drown. And this is actually Blackwater National Wildlife Refuge in the Chesapeake Bay. So not too far, just on the other side of the peninsula. So this idea of ecosystems being able to withstand a certain amount of pressure with regard to sea level rise and storms, but reaching a tipping point where they can be lost is a really central theme to the work that we're doing. And it helps being able to understand that and model that, helps us advise other communities and in terms of how to manage systems so that they don't reach these tipping points. This is an example this is overwash from an island. These are 2 houses on Cedar Island that aren't there anymore. This is 1996 when I first came, right? And so now the island has sort of marched over. Some islands are really good at keeping absorbing the waves, but again, they can get to a point where they stop being able to build dunes, and then they're overwashed all the time by sand and less of a protection to the communities. So one of the things we've been working a lot on is using our understanding of these natural systems and thinking about how to use that to create what we call living shorelines. So these are basically creating habitats that help provide that same sort of protective function. And the 3 that we've been focusing mostly on are the seagrass meadows, underwater meadows I mentioned, marshes, and oyster reefs. And this has been a really strong partnership with the Nature Conservancy. So these are seagrass meadows. This is what I work on. It's like your lawn. Well, it's like a meadow. Like if you didn't mow your grass and you've covered it with water, that's what it looks like here. There's super important habitats for fish, different kinds of fish, crabs and scallops, for example. And the meadows were lost in the 1930s as a result of disease and storms, and they never returned to the area in those coastal bays on the Eastern Shore. And until local watermen found a small patch, and so that spurred this large restoration effort. And so this is the world's largest recognized seagrass restoration. It's over 25 square kilometers right now, which is pretty remarkable. When I came here 21 years ago, you couldn't see a thing. I mean, there was no seagrass. The bottom was just mud. Now you have this, something that looks like this. And so these habitats are really important. This is just a cartoon just to remind me to tell you this. So they're also really important in sort of reducing the energy of waves as they come across those lagoons. When they're absent, you can get a lot of erosion along the edge. When they're present, you get slower energy, and you can begin to build vegetation along the edge. So just like a barrier reef or a marsh, they provide an important function. They're also really good, it turns out. Our lab has discovered that they're really good at taking carbon dioxide out of the atmosphere and storing it for really long periods of time, centuries. And that's one way of thinking about mitigating against rising CO2. And as a result of the research that we did, we wrote the international protocol that's being used for issuing carbon credits on the voluntary carbon market. So the other is the oyster restoration. This is a grad student in our, in our lab. And again, we make oyster reefs, artificial reefs, along the edge of property or marshes, again, to reduce the wave energy that would be hitting the shore and reduce erosion. They look something like this. They're made of concrete blocks, made in Charlottesville, actually, by Allied Concrete, and trucked down. So an oyster reef would look like this when it was first put out, and then it looks like this 3 years later. So not only do you have that sort of that physical structure that really helps reduce erosion, but you also have a living oyster reef that's supporting a pretty highly diverse community. And so I just want to make sort of segue to Phoebe's presentation by making the point that understanding the natural functioning of these systems, using that to sort of develop these living shorelines as an alternative to a seawall, for example, can be used in cities and rural communities as well as it can be used in the natural habitats where we're working. And so this is just a sort of cartoon of where you can, and Phoebe will talk a lot about how she uses some of these ideas. Essentially, you're trying to accommodate some of the flooding water, not just keep the ocean out. And that's a new thing that we've been thinking about in these coastal cities. And these are just some architect rendering. This was an exhibit that was at the Museum of Modern Art in New York. How do you deal with flooding waters? And this is in the Netherlands. And as it was mentioned when we started, we were just, I don't know if you saw in the UVA Today article yesterday, we were selected as one of 2 of the new pan-university institutes that's getting seed money to develop cross-school, cross-disciplinary work on real-world problems like this. And as I mentioned, Phoebe and John and I have been working for several years on developing some of the ideas behind this. So it's a really exciting time at UVA. We have a huge community of people interested in environmental resilience and how that affects people.
a restored biological network with an industrial infrastructure. And I'm not going to go into this project other than to say that it's certainly possible, and the thinking that separates human enterprise from ecosystem restoration is flawed when we see the two as completely separate, because we need both to work together. Out of this project grew a number of stormwater management approaches and things like that, but for me what was most interesting was also the importance of education in any of our thinking about these projects. So as part of a series of 10-year strategies to restore this area, one thing that emerged was the importance of environmental education. Because if we're taking on these kinds of large-scale challenges, how do we help people to understand them, and then also to remain stewards of these landscapes once we have restored them, basically not to pollute them once we've fixed them. So for us, one project that emerged, which for me was an exciting one to do with UVA students, was a floating environmental education center called the Learning Barge. And here the idea was, how could we make a vessel that would adapt to sea level rise, that could move from place to place, as the coastline changed, and that would not be placing undue would not be using any more natural resources than necessary, and could be a model. And so in this case, we were very interested in the relationship between wind and sun and so on. The reason I'm showing you this, it's a little bit peripheral, but I guess my argument is that when students are involved in projects like this at the university, they go out into the world and have a very different attitude about their agency in the world, what they can do, the kinds of things that they're committed to, the kinds of organizations that they might participate in or support. So it goes both ways. It's not just about educating residents and children in the Norfolk area about environmental issues, but also giving UVA students an opportunity to make a difference in the world. And that's, for me, a kind of way of teaching that I've become increasingly committed to. If you want to know more about this project, you can go to the website, elizabethriver.org, and check it out. There's a barge cam. You can see where the barge is as it travels and stuff. But let's focus now, for my remaining time, on issues of sea level rise and adaptation strategies. Clearly, one of the most positive things we can do in terms of natural systems is restoring wetlands and living shorelines. Sometimes that's not so difficult to do. Like in the case of this project, we were working with the city of Portsmouth, with the Army Corps of Engineers and other groups to create a wetland park. And the idea was, let's take abandoned industrial land, which is contaminated, remediate that land, but rather than, in this case, returning it to industrial use, because there wasn't really demand in this particular location, to create a wetland park which could serve the community as an ecological restoration project, but also as a place of recreation and engagement and stewardship. So again, this was a project working with UVA students, and I kind of love this image because this is the wetland before, just after it had been constructed, and what it's like today. And a lot of people now visit this park and have no idea that this was a toxic waste dump, basically. Kids come out. This is an outdoor classroom, which was just finished last summer. And you can get the sense of what it means to be in this environment, which is a beautiful natural environment, but at the same time in this industrial area. What we're working on right now is a project on the eastern branch of the river rather than the southern branch. And it's part of a large effort, about 40 stakeholders, to think about environmental restoration and sea level rise challenges on this branch of the river. And so we were asked to get involved to look at a large district. It's about roughly 40 acres in Norfolk called Harbor Park. If you live in Norfolk, you know this. This is where the baseball team plays. Massive, very low-lying, largely vacant area that is currently experiencing extreme flooding and is immediately adjacent to downtown Norfolk. This is the highway that goes out to Virginia Beach, the Amtrak line, the light rail line. It's also an important gateway to the city. So when this area floods, it causes a lot of problems for commuters and people moving in and out of the city. So we were tasked with the exploration to generate ideas for how this place could become more resilient and adapt. We looked forward by first looking back. And so we were interested in how this place what it was before and how it changed over time. So for instance, this is a map from 1873, which shows, this is Harbor Park. It was basically a tidal tributary to the Elizabeth River heading out then to the James and the ocean. I should say I'm calling it a river. Of course, it's a tidal estuary, so it is coastal. So, you know, of course, this area is flooding because it was a body of water until quite recently. The other thing that we discovered is how this was changing over time. When new uses would come into the city, like the new railway line, this land was filled to make way for that. So often, if we look at cities around the globe, and certainly in the United States, a lot of the most threatened urban areas are areas of fill. I know that's a no-brainer, but somehow cities don't really think too much about that. This is what the area looked like in the 1940s. A very vital, this is it, vital area of shipping and warehousing. This is what it looks like today. Essentially vacant except for infrastructural transportation lines and the stadium. This image shows what a 6-foot storm surge annually looks like on the site. So essentially, there's at least 1 or 2 times each year when that entire site is flooded. The challenge for the city is that they would love to generate tax revenue on this site, but you would be crazy to build here, right, in its current condition. So what we decided to do was look at a series of different resilience strategies that we would then play out and explore in different options on the site. So we essentially looked at, I don't really like these terms, but I'm going to use them anyways today, synthetic or gray strategies, which is essentially concrete for the most part, things like vertical or slope flood walls, earthen berms, piers and jetties, and so on. And we also looked at natural or green strategies like the living shorelines, riparian buffers, wetlands, green streets, different ways of thinking about infrastructure. We were interested in combining these strategies together and not treating them as a kind of dichotomy. At the moment, there's sometimes a little bit of a battle going on between environmentalists who want to use green strategies and sometimes, you know, like the Army Corps, for instance, who might want to use a more and I don't think it has to be one or the other. So what I'm going to show you now are some of the proposals that the students developed. For me, this is cool because these were undergraduate students who did this work. So very high level of research that preceded it and then the work that they generated. So sometimes we think that we can only do advanced research with our PhD students, but I would argue that we can do it at every level if properly managed. Here we were asked to look at that entire site, as well as to design a small, off-the-grid environmental education center. And I'm not going to focus on that today, but just to let you know why you see these small buildings appearing. One thing that we were interested in is, well, you know, this isn't the only place in the world where this is happening. And so we looked at examples in New York and China, places like that, where landscapes could be much more resilient or absorbent. This gives a sense of the overlaying of those maps. This is the original footprint of the city of Norfolk, and then you can see everything in pink has been filled. So essentially, the arguments that most of the students were making is that, you know what, this is not a good place to put high-rise buildings in Norfolk, that there are other places where we can do this, but why don't we think about this land as being a place of essentially a kind of inundation landscape where this part of the city can act like a sponge in many ways to absorb stormwater and so forth. So here you see one scheme looking at a 200-foot wide living shoreline, which protects the development that currently exists. So this land has been regraded to protect this infrastructure. And all that surface parking is put into parking decks. There was also an educational component of these projects. Another strategy looked at taking the idea of using berms, dikes, like the Dutch would do. But the challenge of that strategy is that you cut people off from their waterfront. You know, you can't see the water when you build a berm. This project was looking at how you could integrate the buildings, or at least in this case, this environmental center, with the berms so that it became a kind of gateway and a way for people to get out to the water and experience this floating walkway, but at the same time it could be closed up during extreme storm events and protect that area. And here you can get a sense of that structure. Another strategy that we looked at was that all buildings don't need to be elevated above the ground plane. And that's what you're seeing in a lot of areas right now. that some uses can have lower floors that actually do accept the stormwater when necessary. So in this case, the occupiable spaces are above, the offices and the classrooms, and kayak storage and uses like that are below. So when you do experience an extreme weather event, you basically allow that space to flood, and then you clean it out, and off you go. I'm just going to maybe show you two more strategies that we used. Another idea is bringing the water in, using things like canals and cisterns and ways of holding water on site. This student looked at cities where those kinds of things happen. Or the challenge of not just water coming from the river, but also all the storm water that's running off during these events. And so in this case, the proposal was to create a double kind of barrier, a berm, and also a place to collect water in this dry swale, which sometimes would be flooded and sometimes wouldn't. So I think the lesson that we learn from these projects is that we can't think about buildings or urban infrastructure as static, fixed things, but we need to think about how it can adapt and change over time, and how even the seasons would impact how we use, for instance, a public landscape. So I think I'll end there, and maybe just say that what we're doing at the moment is pushing forward on this work with an economic and legal analysis of some of these strategies with colleagues in the McIntyre School and Urban Environmental Planning. And we're now kind of working our way down the river and working with a community called Ingleside a little bit further down to look at not this kind of huge downtown site, but what do you do in a neighborhood when you have a lot of existing houses and people don't want to relocate, but it's gotten pretty bad right now. So that's the kind of stuff that we're up to. Thanks.
Okay, can you hear me okay? All right, so thanks. I'm John Goodallman, the Civil Engineering Department at UVA, and I want to just build off what's been said already and talk a little bit about what we're doing in the engineering school that's along these lines. Working across disciplines within the engineering school to think about how we address some of these challenges in coastal cities. So you've seen this map already, but I want to expand it a little bit from Norfolk. We're working both Norfolk and Virginia Beach. It's just showing different elevations within these cities. You see why Norfolk is kind of a very important city looking at these types of issues nationally, internationally. It's getting a lot of recognition. It's a great place for us to do these studies, and Virginia Beach as well, and the larger region as well. I want to tell the story a little bit starting with what they're doing now from a civil engineering perspective to think about managing the water in a very adaptive way. This is a neighborhood within Virginia Beach. And these houses here, if I layer on the 100-year floodplain map, you can see that a lot of the roadways, and actually some of the houses as well would be underwater for a 100-year storm. And so this actually happened. So they had, for hurricane or tropical storm Ernesto, there was flooding in this particular neighborhood. The city got together and thought about what can we do to try to prevent this in the future. And they built some infrastructure projects to do that. So here's that same neighborhood. And the way this works here, here's the neighborhood, but there's a series of little ponds. And we as engineers build these ponds to really store that storm water. So the water comes off the landscape, it stores in these ponds, and they're supposed to drain down. So this pond will drain to this pond. There's connections down to this pond, and then eventually out to Stumpy Lake. So Stumpy Lake is a very large lake. It can receive a lot of water. But the problem happens when these ponds get filled up too fast, you get some flooding, and so you don't have that right drainage. So what they've done is go through and do a couple different phases. Build a gate here between the pond and Stumpy Lake, put in some new pipes, some stormwater infrastructure underneath this community so that you can drain it more quickly and efficiently, and also put a pump here on this pond. And the purpose of this pump is to draw down the level in this pond here, push it over to Stumpy Lake so that you can kind of clear the system out. So if a storm event's coming, let's drain it all out, push all that water out, and now we've got a lot of excess capacity within the system to store that rainwater. So here's this pumping station that they built in that community. Here's it operating. And I brought a group of undergrads down that are in a capstone class in civil engineering to take a look at this once I heard about it and heard what they're doing at Virginia Beach. Because this is really interesting stuff. This is not how we normally manage stormwater. But when gravity isn't helping you, you've got to help the water along like this. So this is where that pond drains into Stumpy Lake. So you can see these gates here that they close so that water can't back up into that pond. And then here's the water coming out from the pond into Stumpy Lake during the event. So they're just kind of testing it here and showing how it works. So let me show you a kind of a diagram of how this works. So here's that pond again around all the houses that we want to make sure that doesn't go too high. If it does, then we're going to get flooding. And then here's Stumpy Lake. And we built this little pipe underneath to connect the two. Here comes our rainstorm. Put the gate down, turn the pump on. Stumpy Lake can receive that extra water because it's such a large lake. It's got room around it. There's not a lot of development around it. And that pond doesn't go above that maximum elevation that we want to keep it at. Right, so that's basically how that system works. Once the storm leaves, the lake will go down a little bit. You can basically turn off the pump, open the gate, and those two systems are now connected again. So before the system was built, here's Ernesto again that I showed you before with the flooding of the streets. Got almost 10 inches of rain. And that lake got to about 8.9 feet. The pond also got to 8.9 feet because they're connected before building this whole infrastructure system. And unfortunately, you can't see because it's wrapped, but didn't get above 6 feet after you put that pump in place. So we prevented flooding from that event. I saw that and I said, wow, this is cool. This is the future of civil engineering. Because back at UVA, we were talking about things like smart cities and all these academic terms that we were excited about. Cyber-physical systems, and how can we put embedded computing within civil infrastructure systems to make it smarter and make it work better. And I said, oh, wow, that's a perfect example of what we've been talking about in our research community. So in the civil engineering discipline in general, the idea of making cities smarter, putting more computing in place, all kinds of different examples of that is happening. And here's one example that we're doing in our group with stormwater. So we have real-time monitoring of what's happening in that system. We can even, if roads are flooded, be able to inform drivers ahead of time that we think there's going to be some flooding of a roadway to make sure that people are informed and can make routes efficiently and safely. The devices are on the internet, so they're connected. They know what the weather's going to be in the future. They can kind of operate based on that information. And we have a lot more control, real-time control of the system. We're closing valves, we're opening valves, we're pumping water. All of these things are happening. And so this is part of a larger group in the engineering school that we've developed called this Link Lab. And the real purpose here is to break down barriers within disciplines within the engineering school. Right? So if you're trained as a civil engineer, so I actually am a grad of UVA back in 2001. And when I went to school, you maybe take a couple classes in other disciplines, but more so now, we need these skills. So if you're a civil engineer, you need to have these computing skills to really address some of these real challenging problems that we have. And that's kind of the purpose of this Link Labs. We have faculty members across engineering disciplines coming together to try to work on these challenges of cyber-physical systems. We got an investment from the UVA Board of Visitors through the Strategic Investment Fund to renovate a building in the engineering school called Olson Hall. So we're renovating a space, the second floor, making it a very open, collaborative space where all the grad students across these disciplines can sit together, talk with one another. Because a lot of the innovation happens when those students get together and talk with one another. And the faculty as well have these conversations that break down these barriers. One of the cool things that's happening, and I don't know if maybe you've seen this with even down in the high school level or middle school level, is this adoption of this kind of sensing technology in these little mini computers or microcontrollers that you can program very easily and do really cool things. So Arduino is one that's gotten a lot of attention, things like Raspberry Pi, and there's others as well. And it makes it easy to kind of build smart tools or technologies. So we have students working on these things, even civil engineering students kind of creating new rain gauges that have computer control on it and can communicate the information over the internet. Pressure transducers that we can use to measure heights of water, and humidity sensors as well. And so you can kind of put these together and kind of electrical engineer what maybe would have been typically an electrical engineering idea, but This is a little prototype rain gauge that we created. Right? So you have basically the little mini computer here that can connect to the internet through a cellular modem. Right? And then right here, this is a piezo element. So this is the same thing on your iPhone. When you tap your iPhone, it kind of feels that tapping. And these are only $1 to purchase. And you can program it to actually measure the number of raindrops that are falling. So typical rain gauges are, a couple $100s to buy. Can we get the price down to much lower? Like, can we get it down to $12 or $10? And then we can put rain gauges all over the city and know exactly what's happening. So that's part of the challenge. So this is actually a capstone project from an undergrad in computer engineering at UVA that worked on this particular project. So one of the PhD students in my group in civil engineering is also looking at this problem. And he started off his research thinking about, well, how many rain gauges would we need in a city like Virginia Beach in order to really capture how much rain is falling? Right? So if you want to have the ability to predict if a street would flood or not, you really need to know how much rain is falling at that location, that exact location. Right? So what he first did is to go and find all the rain gauges he could within Virginia Beach. So he went to the Hampton Roads Sanitation District and said, what rain gauges do you have? And pulled all that data. The city of Virginia Beach has their own gauging stations, shown here in pink. And there's also this system called Weather Underground. So I don't know if you've ever been to the Weather Underground website. You can actually set up your own rain gauge and put it in Weather Underground. And then that data becomes available to anyone. And so he also went to Weather Underground and found all the personal rain gauges that are within the region as well, and pulled all those together. So this is everywhere we're measuring rainfall right now. Right? So we know that that's not enough, but we don't know exactly how many gauges we would need. So that's the research that he did to try to figure that out. So what we did first is talk to the city of Virginia Beach and say, well, what are the areas that are flood prone? Where are your problem spots within the city? And they came up back with these locations in particular as locations that frequently flood within the city from a heavy rainfall event. And for each one of those locations, we went and measured what's the watershed for that location. Right? So we found all the watersheds for those locations as well. And then this PhD student's name is Jeff Sadler, as I said on the last slide. He's played a couple games with this data. So here's one of those flooding spots right here. And there's a gauge. There happens to be a gauge right on top of it where they're measuring rainfall. But there's also these other gauges nearby. And so he played a game saying, well, let's pretend we didn't have this gauge. How well could we have predicted how much rain fell on that watershed based on these neighboring gauges? Try to get at that question of, well, how valuable is local information in predicting that rainfall? And so he repeated that over the whole city. And I've got to show you a graph because I'm an engineer. So this is the result from that analysis. And the way to think about this is this axis, just think about that as how much information content is in that rain gauge measurement. And this is how far that rain gauge is from where you're trying to predict flooding. Right? So as you move further and further away from that location, all the way up to 8 kilometers, that information content basically goes to 0. Right? So a gauge 8 kilometers away tells you nothing about what's raining, how much is it raining right here. You really have to get down to within a kilometer, and maybe even within a half kilometer of that location to really know how much it's raining at that place. Right? Because imagine these summertime convective storms that pop up, right? And it could be raining cats and dogs on one street and hardly anything somewhere else. So that's what you're seeing there. So if we had that density of gauges and we put them, just blanketed the whole city of Virginia Beach, we need 500 gauges for that, right? And so this is kind of motivating this work to get that price per gauge down. We're working a lot with Norfolk as well right now. And this is a map that's showing Norfolk. These are all their rain gauge stations. And I apologize, I don't know why it does this when I show it sometimes with PowerPoint. But these are all the rain gauges here. All the blue dots are locations where flooding has been reported by the city on roadways over the last 5 years. You can see all the different locations that roads have flooded from various storms over the last 5 years. This length of line is 1 kilometer. So back to the prior slide, I said about 1 kilometer is what you definitely need for spacing. And a half kilometer would be even better. Right? And you can show that we're really kind of information poor here. So tying back to this idea of cyber physical systems, Internet of Things, we're trying to put our very first step is how can we put rain gauge sensors over this whole city and do it in an inexpensive way. And then from that, we can then get better and better at predicting when we would have flooding events, informing drivers, informing the city, and help the city manage this flooding problem in a better way. So we're also thinking about, in summer, we're thinking about this as really an adaptive infrastructure. Right? We want to be able to manage it on the fly. We want to know what's happening in real time and respond to it in real time. All these smart city concepts that you might have heard of before kind of bring this real-time control to cities. This is one example of how that could benefit cities that we're working on here. And I'm really excited about this session and hearing what Karen and Phoebe said, because all this stuff is really connected. So while we're thinking about it in engineering school in our own way, it really needs this broader context to really address the problem fully. Right, so creating these connections even across schools with these pan-university institutes is a really exciting thing to do. So thank you very much.
So we're hoping to hear from you all. Thoughts, questions, concerns, whatever you feel like talking about, we're here to talk with you. So, or you can talk with each other.
That's a question.
Hi. First of all, thank all of you for doing this. It's a marvelous presentation. In building your riparian barriers, what is the timeline in actually installing one of those?
The oyster reefs, or the oyster reefs within, we get the physical structure right away because it's just concrete blocks. But in terms of a living structure, within a year we've got live oysters on it, and within 2 to 3 years we have a really growing, thriving reef. So it's very short. And we are working with local communities to do it in smaller areas. These were demonstration projects. We were trying to figure out what's the right design. Should it be, how wide should it be? How long should it be? What should its orientation be? And so our idea is to develop some best practices that we can share with communities.
Are you getting a lot of support from the state or primarily from private foundations?
We get zero support from the state, which is interesting. Our support comes from the federal government through the National Science Foundation. That's what's been funding us for the last 30 years. And then the Nature Conservancy gets a lot of money from foundations and private donors.
Thank you.
Who has the next question? So I was actually an environmental science and education major. Yes, from UVA. And now I am at Vanderbilt teaching people to be science teachers. And awesome. Climate change is one of those things that it's written in the standards, but the way our high schools are structured, chemistry teachers say, well, it doesn't fit with us. Biology teachers say it doesn't fit with us. So I'm wondering if you've had any conversation with Curry or schools, or just to get this conversation in high schools where students can start talking about climate change earlier, because I'm in Tennessee, and there's a lot of pushback with this conversation in the schools, as you can imagine, listening to the current political discourse. So I'm just wondering if you've made any progress.
Well, we all probably can respond to that. I guess I would start by saying we're lucky here in Charlottesville. We have a fairly new Environmental Sciences Academy, which is at the Western Albemarle High School. And so students can go there from anywhere in the county that are interested in environmental sciences. So that's great. And anybody can take environmental science classes. My kids go to that high school, and they can take a class even if they're not in the academy. So that's terrific. We actually I work closely with faculty in the Curry School, and I don't know if you all do, we can hear from you, but we actually, at our research program, we actually have, we get a little bit of funding to have what we call a schoolyard program. So it's part of what we do, is we work K through 12. Develop curriculum, give them field experiences. A lot of these kids have never been out on a marsh. We have teacher training programs, so we bring teachers in, we train them, they go off and teach that in their high schools. And then we also developed our Curry colleague has developed 2 online teaching modules. So we use that to sort of have a broader reach. So I would say that that's something that's really central to what we do, through environmental sciences on the Eastern Shore, but I'm sure the others have things to say as well. But I completely agree with you. It's something we need to address early on.
Mm-hmm. Yeah, I mean, I agree with that. Most of my involvement seems to be in Norfolk area at this point, but we have this year it's a 3-year grant from NOAA, the National Oceanic and Atmospheric Association, to develop a resilience program for children in that area, K through 12 kids. And so I'm working with the Elizabeth River Project and Old Dominion University and other partners on this grant, where the Learning Barge, which started out with a particular curriculum that was much more about wetland restoration, oyster reef restoration, and it still is, but we become very much more concerned about how do we get climate change and sea level rise into that discussion. And so we're now working to, actually we're almost done, working to develop a middle school curriculum. Now the challenge is not every kid in that area comes to the Learning Barge or to Paradise Creek Nature Park. But right now, we're lucky in Virginia because there is the meaningful watershed experience requirement. I don't know if that will continue, but it's not that hard to get kids out. Like right now, every 4th grader from the city of Portsmouth comes to Learning Barge and learns about environmental resilience. But that's only 4th grade. And so next year, we're focusing on high school. But I think a lot of times people don't realize how much of a strong connection there is often between universities and K through 12 education. And I think that's really important for a public institution like UVA, where we do have some obligation, I feel, to serve the state in some way, even though we're not getting a lot of funding from them.
Yeah, I'll just add, I think it's really important. I'll just add that I think, from my experience at least, the sea level rise is a little bit easier of a topic to talk about sometimes, which doesn't help you in Tennessee. But this is something that, even the city of Norfolk, even maybe 5 years ago or longer, this wasn't something that was really allowed to be talked about, as I understand, talking to the engineers there. But now it's the topic, and they have an Office of Resilience, and they're kind of all in terms of thinking about of sea level rise. And I don't know why that is. Maybe it's easier to see, and than climate change. It's a little more concrete, but that's been my experience.
Oh.
Right. Mm-hmm. So more extreme flooding those happen so infrequently that it's hard to build a conversation around it.
I think any global phenomenon, it's hard for a lot of people to want to think about it until they experience it directly, and then it becomes real.
So building off of that, kind of a two-part question, instead of the kids, the politicians. So I have a community where there's a big battle going on between the fishermen and a real estate developer, and whether or not they're going to zone and allow the developer to come in and disrupt the mangroves, the seagrass. So I guess, are there programs or organizations that can educate those town councils that vote on zoning? And then the second part, you're talking about kind of remediation, what to do afterwards. Are there things to require developers to do? Oftentimes they say, well, you can cut the mangroves there if you go remediate it somewhere else, or you do something else to balance it. Have you guys are there groups doing studies on that trade-off? What are good trade-offs? Are there resources?
Well, I think, I guess I would say that they're going to vary depending on your location. And for the most part, they're going to be location specific. I mean, there are sort of more national resources. But for example, in our work, we're part of a group that includes all the planning commissions, the local planning commissions. And it's not, and the nonprofits that work in the region and the different universities. You're right that it's not an easy conversation, and sometimes you're surprised by the concerns. But we are doing work where we're bringing stakeholders in early in the process. Phoebe's doing the same to help sort of define the problem, the question, get the get the engagement and try to figure out together, how to move forward. And I think to the point of the institute that we're creating, that's really at the center of it, which is to build these collaborative groups that include what I would call the end users, the people actually are using the information, as well as the researchers, and co-develop the ideas and the methods and agree on what the goals are. And so that's something that's challenging. That's why we propose to create an institute to do this. But it's also the possibility of having the biggest impact.
Mm-hmm. Yeah, and I would say that for me, the groups that have the most success are often the local NGOs, whether it's a small watershed group like the Elizabeth River Project or the Chesapeake Bay Foundation that's functioning at a much larger scale, because they're on the ground. And so we can go there and be part of that discussion, and it's pretty valuable. But being in the community, living in Norfolk. And I guess I would also say, with the politician issue, that working with communities and empowering small-scale communities is one really positive way, because they do elect those folks. And so sometimes I am just a real believer in grassroots action in that way, because if people like in Norfolk are concerned about their homeowners insurance, huge issue. And so if they understand what's happening, they're going to be much more concerned about being active in their local government, in local zoning decisions, in the people that they choose to represent them. So I don't think there's a quick way to solve the problem, but I think it's just more engagement across the board at every level, which is hard, but I think that's what we have to do.
I wanted to ask Professor Goodall, so is Virginia Beach, one, is the topology such that you can actually manage ahead of time stormwater so that you can pump? Do you have places to pump the water to be able to make an effective sort of overall evasive plan for floods? And before you answer that, I wanted to ask you, I remember a couple of years ago reading somewhere, probably in the New York Times science section, that in the Chesapeake Bay and Eastern Shore regions, that the sea level rise is, that the situation's exacerbated because the land itself is sinking. Mm-hmm. And in fact, that's about as big an effect as the sea level rise so far. Is that correct? And lastly, you can get people's attention when you tell them how much sea level rise there'll be when you melt the polar ice caps.
Right, yeah. So thank you for that question. So it is true, we should have said that. The subsidence issue, the sinking of the land, is roughly equivalent to the sea level rise. And that's a whole other challenge. And that's a challenge that's being addressed within the region. So anyone that lives in that region has probably heard of this project of taking wastewater, treating it to drinking water standards, and injecting it into the aquifer. And so that's something that's happening right now in Hampton Roads with the Hampton Roads Sanitation District. Very large project. It's been done in other places in the world. It's done in the West Coast. It's been done in kind of the Southern California region, but this is the first example of this in the East Coast. And one of the things they're hoping to do is to at least slow that process by pumping water into that deep aquifer, because part of the reason that it's sinking is drawing water out of the aquifer and then kind of compressing over time. So you're exactly right. That's also part of the challenge. And the other question you had about can that example of kind of draining the water out of the lakes in this one community, can that be replicated to others? That's a great question. That's one of the things that we want to look at in our research. Where are the locations where that strategy could be used, such that the drainage is kind of set up in that nice little sequence where you drain one pond, it drains 5 other ponds. It's certainly not everywhere in that region. The other places they're putting pumps in Virginia Beach are basically on the shoreline and pumping the water straight out to the ocean. So that's the other kind of strategy, is to kind of draw down local ponds and just get the water out to the ocean as fast as you can. But I think it's a reasonable strategy. It's very expensive to build these pumps, so I don't know exactly how scalable it is. But you have limited options in some sense in terms of the groundwater table is so high, and the lakes are so high. There's just nowhere for that storm water to go. right? And so you're just trying to create room for it. And that's one approach that they're using now. That their strategy at least is to continue to do that for the next few years. At least that's one of their main strategies for fighting the flooding problem.
Just wanted to add one quick thing that John could talk more to, but I think we often forget that it's not just what rain is hitting, but it's coming down from rivers and flooding these areas. And so we saw with Hurricane Matthew, the biggest flooding wasn't during the storm, but it was the rain that was coming down the river a week afterwards. And so that's an important part of what you're doing as well in terms of the engineering solutions.
Right, yeah, it's a really difficult system because you've got the groundwater table really high at certain times. You got the tide. If the tide's really high, you might get a different response. You've got storm surge happening. You've got rainfall happening. You've got to think about all that together. Exactly right.
It might not be the best place to live in some ways, but
No, it's beautiful.
that's another discussion.
There's a question there. Yeah.
Hi, thanks for the presentation. It's really interesting. One of the things post-Sandy, and I live in New York now, that was put forward by Rockefeller Foundation and HUD was Rebuild by Design. And there were 10 different awardees and different projects in the area. And I didn't know if there were any takeaways from that. Where are we today? The Big U, Bjarke Ingels Group with the southern tip of Manhattan and so forth, taken over. So one of the images looked something like that. I didn't know if there were any specific developments from that effort that you find applicable or particularly interesting, and so sort of an open-ended result. But it is something that a private foundation, other than the ones you've mentioned, has actually jumped right into with Rockefeller. I thought it was kind of commendable. So interested to hear.
Well, I think one good thing is that Norfolk was selected to be one of the 100 resilient cities through the Rockefeller Foundation program. I think the challenge, there are a lot of takeaways from the work that's been happening in New York, but a lot of it is so expensive. Actually, it's all expensive. And so I think one of the biggest challenges for the Norfolk Hampton Roads area is that the density that we find in lower Manhattan, which can pay for that kind of infrastructure, is not in place in a city like Norfolk. And so, there's always a cost-benefit analysis and who pays for it. And I feel like that's one of the biggest challenges, where even in a city like Miami, there's more, there's more density and more tax revenue to pay for that. The thing that we do have happening, though, in Norfolk, or a positive, is the huge military presence and the fact that the Navy is very concerned about these issues and does have resources which could be, which are being put into play, at least in some areas. So yeah, there are a lot of great ideas out there, and it's not just in New York. I mean, we looked at case studies all around the world. Really cool work being done in China, of course, in the Netherlands, Germany, and all over Europe.
Was that?
Yeah. The issues that the discussions we've been having with the city, though, it always comes down to money, of course. And none of this will be free.
I mean, I think as a non-urban person, as a coastal ecologist, I think one of the things that's striking to me is over the last decade is this changing sense that you're not going to hold back the sea. You just have to figure out clever ways designing urban systems where you accommodate flooding water. And there's the Europeans are way ahead of us in this, but there's lots of interesting things, and that's part of what these groups are working on, is trying to figure those out.
Yeah, I think it's fertile ground for creative solutions, at least in civil engineering. So I think that it's great to engage students across all levels. So I've got a group of capstone students in civil engineering that are going to be focusing on this in the fall semester, and just bring your creative juices to this. What do you guys think we can do here to try to really store this water at certain times? So just the difference with tide in that region. I mean, there's basically no real issue at low tide. So can you hold all that water and just release it at low tide? Just different strategies like that can make a big difference.
And sometimes we're going to have to make trade-offs too, between maybe every single square footage of the city can't be protected to the same level in the same way.
Right.
And we have managed to build in areas that are very vulnerable and problematic. And so when you look at the coastal development and a lot of, Kitty Hawk and down there, I mean, there are places where we really should not be building houses. And it could be that some of those communities, cannot continue in their current location. And no amount of engineering is going to solve that.
Sorry, John.
Yeah, sorry. No amount of design is going to solve that, right? I mean,
Nature.
Yeah, Karen's nature folks are
Well, on that note.
nature.
Well, please, this was extremely interesting and sort of local, very local interest. And please help me thank Karen, David, and
Thank you.